Some places don't kill you, they rewrite you. You skim the blue edge of Neptune, expecting gentle drag, a clean bite of atmosphere, a controlled bleed of speed. Instead, something starts to hammer the hull in a fast, granular rhythm, like a pressure washer loaded with grit. It is not debris from space, it is the air itself turned into a sandblaster by wind. You have heard the headline, that Neptune has the fastest winds in the solar system, that it is cold, distant, and quiet. Quiet is the lie your instincts invent to feel safe. Out here, quiet only means you cannot hear the machinery until you are inside it. In the next few minutes, you will learn why Neptune's winds can reach around 2,100 kilometers per hour, why that matters more than temperature, and how a spacecraft can be damaged without ever touching a solid surface. Because this mission is not a plunge, it is a brush. A shallow pass through the upper atmosphere to taste the planet, to steal a few minutes of data, to use the air as a brake and save fuel. And if you think the danger is heat, you are thinking like someone who has only flown near worlds with ground. Neptune has no ground to hit. It has something worse, a moving fluid that behaves like an instrument. Neptune is an ice giant, but that word is misleading. The ice is not a frozen crust you can land on. It is chemistry under pressure, water, ammonia, methane, locked into a deep interior that does not care about your definitions. Above it is an atmosphere made mostly of hydrogen and helium, with methane as the trace that stains the planet blue. Up at the cloud tops, the temperature can sit around -220 degrees Celsius, cold enough that methane can condense into ice crystals, cold enough that hazes form, aerosols suspended like dust in an endless sky. On Earth, wind is mostly a problem for aircraft because it changes your lift. Here, wind is a problem because it changes your relative velocity. Your spacecraft is already moving fast, orbital fast, a knife edge between falling and missing. Then the atmosphere itself moves in bands and jets, sometimes in directions that do not match your approach. Voyager 2 saw it first in 1989, tracking bright clouds as they raced across the planet. Later, Hubble watched giant dark storms appear and fade and measured how the wind fields guide them across latitudes. Neptune doesn't get much sunlight. It should be sluggish, but it radiates internal heat, and its atmosphere responds in ways we still argue about. The result is a world where the air can outrun sound in some layers, and where storms can be the size of Earth. The mission plan is elegant. Too elegant. Your vehicle is not meant to descend, it is meant to dip. The pass is called an aerograb, a shallow bite of Neptune's upper atmosphere to reduce velocity, tighten the orbit, and let the spacecraft linger longer without carrying impossible amounts of propellant. You come in over the terminator, where day becomes night, where the planet is a gradient of cobalt and ink. The instruments wake up. Temperature, pressure, composition, particle counts, all of it starts as numbers. Numbers feel safe. At first, the drag is exactly what the simulations promised. The craft shudders softly, like a hand on the shoulder. The plasma sheath is thin. Communications flicker, but do not die. Then the wind finds you. Not a gust, not turbulence, a sustained lateral flow that turns your forward motion into a diagonal. You are no longer cutting through still air, you are cutting through a river that is moving sideways at hundreds of meters per second. Relative speed spikes without warning. The particle counter climbs. The haze is thicker here. Tiny solids, ice grains and aerosols suspended in a cold pressurized soup. Each one is small, harmless in isolation, but at high relative velocity, size stops mattering. Kinetic energy does not care if the projectile is a pebble or a grain. You feel it in the telemetry first. Surface temperature on the leading shield rises not only from frictional heating, but from impacts that convert motion into heat at microscopic points. Then you hear it, translated by structure sensors into audible range, the hull's skin responding like a drumhead. Tap, tap, tap. Then faster. A hard hiss. The first abrasion alarms light up. Not catastrophic, not yet. Protective coatings that were meant to survive radiation and micrometeoroids begin to pit, because this is not random impact from space. This is directional, sustained, and dense. A sandblaster is not powerful because each grain is strong. It is powerful because it does not stop. Your star trackers start to complain. The sky around Neptune is no longer a clean field of points. It is smeared by the planet's own aerosols, a soft scattering that makes the universe look slightly wrong. The craft asks for attitude corrections. You comply. Reaction wheels whine. Thrusters puff, tiny clouds of gas that vanish instantly. Another layer, another band. The wind shear changes again. It is like crossing invisible rails, a push, then a pull, then a sideways shove that tries to roll you. The vehicle is built for aerodynamic stability in thin gas, but Neptune's winds are not a single direction. They are stacked, moving strata sliding over each other. At 1 bar on Earth, you can stand and breathe. Here, 1 bar is only a number on a pressure plot, a place where the atmosphere has density, where particles can behave like real projectiles. You were never planning to go that deep. Neptune does not ask what you planned. The storm is not visible at first. It is a change in the color of the light, a slight darkening below, like a bruise under skin. Instruments register a pressure gradient, subtle but present. Winds accelerate along its edge. You are entering the flank of a dark vortex, one of the transient giant storms Neptune makes and destroys on timescales that feel personal only because you are fragile. The lateral wind climbs. Your guidance software tries to keep the angle of attack within limits, but the atmosphere is moving too fast relative to you. The craft's nose is forced to hunt, correcting, each correction spending precious control authority, each moment increasing the chance of a tumble. The impacts intensify, not taps now, a sustained rasping like a file dragged across metal. A panel sensor spikes, then goes dead. A second later, another sensor reads a temperature drop that makes no sense until you realize what the sandblasting is doing. It is stripping a surface layer, exposing colder material beneath, changing emissivity, changing how the craft radiates heat. Your thermal model loses its grip on reality. The craft reports microfractures in a ceramic layer that was designed for smooth aerodynamic loads, not for high-speed particulate erosion. You remember that sand on Earth can carve stone given time. Here, time is compressed by velocity. Minutes become years. The storm's edge grabs you. Wind shear rolls the vehicle a few degrees. The reaction wheels saturate. Thrusters fire harder. A thin line of propellant that was meant for months of gentle corrections is now being burned in frantic bursts. The particle counter is no longer counting cleanly, it is pegged. The air around you is thick with suspended ice and haze. A craft can survive heat by spreading it. It can survive pressure by resisting it. But sandblasting is betrayal at the surface. It turns protection into weakness by removing it. The leading shield is still intact, but the coatings that prevent charge buildup are eroding. Static changes. Plasma interacts differently. Communications drop into a stutter. For a few seconds, you are blind, alone in the blue. Then the craft regains link, and it sends a frame from an external camera. The image is grainy, not because of low light, but because the lens itself is being frosted by impacts. The planet below looks soft and smeared, like you are seeing it through scratched glass. You have a choice now, and the choice is brutal because it is simple. Continue the pass and complete the sampling run, or abort and climb, burning fuel you cannot replace. You came here for data. Neptune is turning your craft into data. You command the abort. The engines fire and the craft tries to climb out of the dense layer into thinner gas, into safety. But the wind is still there, still pushing sideways, still forcing your vector into something you did not design. The craft rises through a shear boundary, and suddenly the impacts change pitch, a higher, sharper hiss, as the particles become smaller but faster, like a finer grit at higher speed. One more spike, a sharp shock through the frame. A piece of external insulation tears loose. It does not float away gently, it is shredded immediately into fragments that vanish into the haze. For an instant, you understand what no solid surface really means. Neptune can erase hardware without ever letting it hit ground. It can grind you down in open sky. You clear the layer, the craft stabilizes, the particle counter drops, the rasping stops. The silence that follows is not relief. It is the sound of a problem that has moved inside you. In the hours after the pass, you inspect the vehicle through its remaining cameras. The leading edges are scarred, coatings are patchy. Some surfaces look matte where they should be reflective. Others look glazed, as if they were polished by violence. The damage is not dramatic in one place, it is everywhere in small ways. 1,000 tiny losses that add up to a new spacecraft. And the data, the thing you almost died for, is terrifying in its normality. Wind vectors that spike beyond what your models predicted. Aerosol profiles that suggest layers of particles you assumed would settle out. Temperature inversions that hint at energy transport you do not fully understand. You label parts of it as hypothesis because you have to. One possibility is that the worst sandblasting happens in specific bands where methane ice particles and aerosols are concentrated, and where winds accelerate along pressure gradients near storms. Another possibility is that your craft created its own hazard by shocking the local flow, lifting particles into the path of your leading edges. Either way, the principle is the same. At Neptune, wind is not background. It is an active environment. It is a moving weapon made of gas and suspended ice. And the cruel part is that it is not even trying to be cruel. Neptune's atmosphere does not have intent, it has physics. You can design for radiation, you can design for micrometeoroids, you can design for heat and cold. Designing for an atmosphere that can throw its own particles at you at extreme relative speed is something else. It is like designing for weather that acts like erosion, but on the timescale of a single breath. You think about future missions, about probes that might try to dive deeper, to taste the chemistry beneath the clouds, to listen for magnetic signatures in the ice giant's interior. You imagine them entering these layers and staying longer than you did, trusting shields and models and optimism. And you realize that Neptune does not punish optimism. It simply reveals what it costs. When you finally pull far enough away that Neptune becomes a perfect blue coin again, you feel the temptation to call it beautiful, to pretend beauty is safety. But you remember the hiss, the granular hammering, the way your spacecraft changed under invisible wind. You remember that this planet can sandblast you without rocks, without sand, without ground. Only particles and speed and time compressed into minutes. If you want the next tape, subscribe. The archive keeps growing. Science you can hear, dread you can feel. Because out there, beyond the comfortable worlds, the universe does not need monsters. It has motion, it has pressure, it has wind. If you heard it, would you answer?